Hello advanced physics students, this is Dr. Brenz here, and this is a supplementary video on lesson 2.2.3, which is the lesson about friction. There was some confusion in class about the kinetic, the coefficient of kinetic friction here, so I decided to make this video and show you guys what I came up with, and then you can compare to see what you came up with and figure out where you might have gone wrong, or to confirm that you got it correct. Alright, so what I have here is I have a 15 kilogram block and a 50-degree incline, and we know that this block is accelerating at a rate of 2.5 meters per second squared. So I'm going to redraw that block right here to give myself some room to work. And it's always a good idea to start off by drawing free body diagrams. So I'm going to draw a free body diagram of this block. We have gravity going down. We have the normal force going perpendicular to the surface. We have friction going to the left. And we need to break down this gravitational force into its x and y components. And sometimes it's hard to figure out the angle, so I decided to draw a dashed horizontal line, not part of my free body diagram. And I know that if the angle is 50 degrees in that triangle, then also this angle right here also has to be 50 degrees. And if that's 50, then this angle's 40, and this angle's 50. Alright, so hopefully that convinces you that this angle inside our triangle, where we're breaking up the gravitational force, is 50 degrees. Well, we do some trigonometry, do our SOHCAHTOA. We know that the adjacent side is cosine and the opposite side is sine. Now I'm going to redraw this free body diagram, but this time with the forces already broken down into their components. So I have f sub g cosine 50 degrees going down in the negative y direction on my new coordinate system, and fg sine 50 degrees going in the x direction on this rotated coordinate system. Okay, have a free body diagram. It's usually a good idea to write down Newton's second law for each of the directions. So for the x direction, F net equals ma. For the y direction, same thing. And when I replace F net with all the forces in the x direction, I sum up the forces in the x direction, keeping track of signs. I get negative F due to friction plus F sub g sine 50 equals mass times acceleration. Right. And we know the force due to gravity is mg, so I'm going to plug that in. And then I know that m times g is 15 times 9.8, and I know that the acceleration is given to me as 2.5 meters per second squared, and that is in the x direction. So I plug that in for acceleration down here. Do a little simplifying right here, do a little evaluating, and it tells me that the negative f sub f plus 112.6 equals 37.5. Alright. I could probably do a little bit more than that. Yeah, I could actually figure out what the friction force is, and it turns out to be 75.1 newtons. Right, but that doesn't help me, because what I want to find out is the coefficient of kinetic friction. And in order to do that, not only do I need the force due to friction, but I also need to know the normal force. Well, we'll probably get normal force out of our y equation here. So let's now turn our attention to F net equals ma in the y direction. I forgot to press my button and remind you guys that the friction force is equal to mu, our coefficient of kinetic friction, times the normal force. And this is what I don't know yet. This is what I want to know, but I need to know this in order to get to know that. Right. And that's why we're going to the y direction here. Alright, so now that we have that established, adding up all the forces in the y direction, F sub n plus negative F sub g cosine 50 degrees equals mass times acceleration. But am I accelerating in the y direction here? No, I'm not. So that's going to equal 0. And of course, the force due to gravity is equal to mg. So I replace that, and it turns out normal force minus 15 times 9.8 times cosine 50 equals 0. Do a little simplifying here, solve for F sub n, and I find out that the normal force is equal to 94.5 newtons. Okay, plug that in there, and I find out that my coefficient of kinetic friction ends up being 0.79. Okay, so that was that whiteboard practice problem. I'm guessing usually the most common mistake that people made in this problem is that they didn't realize that the normal force is equal to only the gravitational force component in the opposite direction. Okay, we know that our normal force is pointing up, but it only balances the gravitational force in this direction, which is F sub g cosine of 50 degrees. A lot of people will try to put just force due to gravity and forget the cosine part, and they'll end up with a value that's different than what they should get. Okay, I did also promise to show you how to do the mastery check number 2, especially since we didn't have enough time during class, and a lot of the homework problems depend on being able to do a type of problem like this. Alright, I am going to change a couple things here, because what I didn't realize is that, well, first of all, we have this thing in motion, so it is kinetic friction, not static friction. And I also have to change the mass of this purple block here to 9 kilograms. The reason I had to do that is because if I leave this at 4 kilograms and I work out this entire system, it turns out that the block accelerates down instead of accelerating up like I was hoping it would. If I didn't have friction, that wouldn't be such a big deal. I would just say, oh, well, that means the acceleration has to go the other way. But if the block is moving that way, then my friction force has to go that way, and I have to do my problem all over again. So rather than do that, I'm just going to change that mass to 9 kilograms. Okay, so I have a little diagram up the top left-hand corner, same one that you saw on your screen. Let's fill in some numbers. Mass, the two masses. Let's remind ourselves that the coefficient of kinetic friction is 0.3 and that this angle is 40 degrees. Alright, always a good idea to start off with free body diagrams. Free body diagrams. So let's draw those free body diagrams for these two masses. For my 9 kilogram mass, it's pretty straightforward. I just have tension going up, gravitational force going down. For my 5 kilogram block, I have to create a rotated set of axes, x directions going along the incline. I have gravitational force still going straight down. I have my tension force in the rope pulling it to the left. I have my friction force resisting that tension. And I have the normal force perpendicular to the surface. Alright, this gravitational force is the only thing that is not along the y-axis or x-axis. So I have to break it down into its components. And when I do, it turns out that since this angle is 40 degrees, this angle, or this component is f sub g cosine 40, this component is f sub g sine 40, and I have to add that to the force due to friction. Okay, now that I have those free body diagrams set up, let's go and write down Newton's second law. Let's write it down for the 9 kilogram block. F net equals ma. It's just tension minus gravity, and that is equal to m times negative a. The reason I put negative a in here is because I am expecting the block to accelerate in the down direction. And let's go ahead and start filling in some numbers. Turns out that the gravitational force of a 9 kilogram block is 88.2 newtons. And I can also fill in the mass. Alright, and I can't do anything more with that, so let's go on to the 5 kilogram block in its x direction. Write out Newton's second law. And Newton's second law just says that the sum of all these forces is equal to mass times acceleration. And again, I'm expecting the block to move to the left. So I am going to write this as negative a, negative acceleration. Okay, let's now turn our attention to the 5 kilogram block in the x direction. So in the x direction, let's write Newton's second law, F net equals ma, and we're going to add up the total of all the forces in the x direction. And we're going to set that equal to m times negative a, and the reason I wrote negative a is because if our 9 kilogram block is going to accelerate down, the rope is going to force the 5 kilogram block to accelerate to the left, which is the negative x direction. So that's why there's a negative sign there. Okay, well, let's go ahead and start replacing some of these things. So I can replace the friction force with mu times the normal force. And I can replace F of g, the gravitational force, with mass times the gravitational acceleration, 9.8. And let's see, let's go ahead and start plugging some numbers in here. I know that the friction coefficient is 0.3, and I know that mass times gravity will give me 49 newtons. And finally I have the mass over here on the right hand side, 5 kilograms. Let's do a little simplifying here. I know that 49 times sine 40 is 31.5. It looks like I am stuck at this point, and it looks like I have two equations, but I have two unknowns here. And I have not only those two unknowns, but I have this, which is a third unknown. Okay, so we're not used to seeing that. But we still have the y direction on the 5 kilogram block, so let's go ahead and write that one out. F net equals ma. Let's write out what the F net is. It's the normal force plus negative force of gravity times cosine of 40 degrees. And we're going to set that equal to 0 because there is no acceleration in the y direction. Let's plug in some... Oh, actually I decided to solve for the normal force by adding f sub g cosine 40 to both sides. And I can replace f sub g with mg, and mg for the 5 kilogram block equals 49. So I can say 49 cosine of 40 degrees. So our normal force is 37.5 degrees. Alright, I have to write all this out. Actually, woo! I did not mean to do that. Let's see, I meant to do this right here. Okay, so this is where we left off. Right. Okay, I needed to give myself some more room, so I had to create a new slide here. Okay, now that I have this normal force, I can plug it into here. Let's do that. And let's do a little simplifying. And voila. So now I have this equation with tension, force, and acceleration that are unknown. This one has tension, force, and acceleration as unknowns. So I have two equations, two unknowns. And I want to figure out the acceleration of the system. So I want to solve for f of t right here, f sub t, the tension force. And then I am going to substitute that in down here. And when I do that, I now have an equation that just has acceleration in it. I do some simplifying, and we will see that our acceleration is 3.2 meters per second squared. Alright, so that block, the block that was freely hanging, it will accelerate down at that magnitude, 3.2 meters per second squared. And our block on the incline will accelerate up and to the left at that same magnitude, 3.2 meters per second squared. Okay, now that you know how this would go, you will be able to solve a lot more problems on the homework, I hope, and I'm looking forward to seeing your work tomorrow. Take care, bye.